Right, so this is 2008 question 22. Creative mass 40 kilograms, pulled up a slope using a rope. Up a slope. Make sure you notice it's up and doesn't not down. Okay? A mistake can be made when you say, oh, you think it's actually going down, it's actually going up, and there's your mass there as well. The slope is at an angle of 30 degrees to the horizontal. This means this angle here, if you were to draw your little vector addition, the 30 degrees would be at the bottom. A force of 240 newtons is applied to the crate parallel to slope, right? Pulling it up the slope, 240. The crate moves at a constant speed of 3 meters per second. Here is the word that's important. Constant speed. 3 meters per second. Oh, yeah. Okay? Right. Calculate the component of the weight of the crate acting parallel to the slope. So you're looking for the component of weight acting this way. Parallel to the slope. You draw your vector diagram. You have weight acting down. You have parallel to the slope, and you have into the slope. And it's a right angle triangle like that. So this is your W, this is your 30, this is the weight parallel to the slope. That's the one you're looking to calculate. W equals mg to give you your weight, and you just use trigonometry to get, or Pythagoras, to get your weight parallel. So you will get that as a value in newtons of your weight coming down the slope. 2 marks for that. You get 1 mark for probably working out your actual weight itself, and then 1 mark for getting the component correct. Okay. Calculate the frictional force acting on the crate. Right, and this is where this word comes in. Constant. If it is constant speed of 3 meters per second, what must be the force opposing the motion of the crate, Carson? 240 newtons. There must be 240 newtons opposing the motion of the crate. Okay, so there must be 240 newtons pushing back that way, and that's why the forces are balanced, because it's a constant speed. An object either remains at rest or travels in a straight line at a constant speed unless acted on by an unbalanced force. That is Newton's first law. Okay, so if 240 newtons is pulling back down, the component of weight you've already worked out as a number. That's acting down as well, so whatever's left over from the weight acting down must be the friction. So you take the weight parallel, this here, off the 240, and whatever's left over must be frictional effects of the slope. Ross?
How would you get too much?
Pardon?
Why is that worth too much?
Probably for identifying our balanced forces to start with. Forces are balanced, constant speed, and then doing a subtraction.
Probably, so all the work you need to write is subtraction.
And the balanced forces, you need to identify that the forces are balanced.
Oh, that's what you say.
You need to say the forces are balanced. Okay? Right. Finish that off. We've already had 4 minutes, or how many minutes did I give you?
4.
3? Right. Just finish that one off. Give you another, just another minute or so, couple of minutes. 2 minutes to finish that off.
Finish what?
Just that question, you've not finished that bit.
Yeah.
Uh-huh. We have here F equals mg sine theta, so your force parallel to slope should be 196 newtons. Okay, half mark off if g is 10, but you should know that by now, it's 9.8. Second part is you're saying forces are balanced, that gives you half a mark. Or that it is mg sine theta equals a frictional plus a frictional force, and then you're getting 1.5 marks for working it out. You're saying 240 must equal 196 plus F force of friction, so force of friction is 44 newtons. So you're getting half mark for saying it's balanced forces, and then 1.5 for getting the question for actually doing a subtraction. Dead easy. Okay? Right, so let's look at the rest of the question. Okay, you've got, as the crate is moving up the slope, the rope snaps. The graph shows how the velocity of the crate changes from the moment the rope snaps. Describe the motion of the crate during the first 0.5 seconds after the rope snaps. Worth 1 mark. Okay, you hardly need any time at all to think about this. What you're doing is trying to interpret what the graph is telling you here. Right? The rope is snapping here, but somehow the velocity is below the axis. So what does that mean about the motion of the object down on the slope? Fraser? Accelerating down the slope. Good. Now the way you can think about that is you've got a sign convention. You've already said that up the slope is positive. Therefore, if it's coming down the slope, it's going to be negative.
It's only talking about the first 0.5 seconds.
Alright, sorry. Describe the motion of the crate during the first 0.5 seconds after the rope snaps. So that's going to be it coming. That's going to be it snapping. Okay.
No, it starts snapping.
It
from
snaps
zero.
at the very
It snaps
start.
and then the
Oh,
velocity
right,
has to
right,
go
right.
to 0 and then
Right,
start
okay.
moving.
Okay. Hang on. Right, let me just read the question again. Always read the question. Graph shows how velocity crate changes from the moment. Sorry, the rope has snapped here. Right, my mistake. Rope has snapped here. Okay. At this point here, something happens, and then it goes down the slope, like Fraser said. What's happening between there and there? David, colour.
It slows down.
Slows down. So starts off at 3 meters per second. It slows, it stops, then comes back again. So the thing's going up, it's stopping, and then coming back again. So between 0 and 0.5, the object is slowing down to rest. Okay? Right. Let's keep going.
We've only got a few minutes.
Sure we'll manage. Right, okay, copy the axis shown below and sketch the graph to show the acceleration of the crate between 0 and 1 seconds. Approximate numerical values are also required on the acceleration axis. Right, so that's 2 minutes. Right, stop there. We'll finish this off.